No problem, we can do that. So on this one, which we saw problems like this on the previous homework, I know that I'm going from 45 down to 5 because I got to go from 63 down into whatever x is. Since I'm making 45 smaller, that means I'm going to have to use division. Divide by what? Well, in order to make 45 a 5, I'd have to divide that by 9. So I'm going to take the 63 and divide that also by 9. And when I do that, I get x equals 63 divided by 9 is 7. So if you replaced x with 7 here, you would get a true statement. There's our objective for the day. I can force denominators to match so that I can add and subtract fractions. Take 30 seconds and copy that down, please. All right, one of the key words in the objective here is force. Because most people hate fractions. In fact, fractions have been known to destroy people's lives, which we don't want to happen to you, so we don't let it. But in order for that to happen, you have to take control of the fractions themselves, and you have to force the denominators to match, okay? So just like we've seen in the past, we've had to scale the fractions, whether it was up or down, in order to force values in fractions to match, okay? So this will mean that we are not changing the value of fractions, only the way that they look. That is all we're changing, okay? Remember, for example, that you could have 1/2. You could change the way it looks into 2/4. That does not change its overall value, though. But right now, the objective is, particularly with denominators, in order to add and subtract the fractions, you have to have denominators match. We'll be able to force that after the lesson's over. So as we can see here on this slide, you need denominators to match in order to add or subtract. And that's what the B is showing. It's just, B would be some kind of number. And when that happens, we kind of make it into one big fraction like this by adding the two numerators, okay? Now you can add, you can subtract as well. But we'll remember with subtraction, if we ever see negatives like that, we don't actually subtract with negatives, we only add with negatives, which may require some keep, change business. And as long as you remember that, that's good, okay? Now, while we're getting used to adding and subtracting fractions, I would recommend not skipping this step. Although in the future, once you get really proficient at adding and subtracting fractions, you may not need this step, as I've seen not only with students your age, but also college students as well, okay? So, if you think about this, the denominators, if we had denominators of 5 like this, let's say we were adding, then what we do is we make a big old fraction like this with addition, and then whatever the numerators are, that's what you add. The other thing with fractions is if you ever see a negative fraction like this, let's say it was, 4/7 like this, okay? When we go to add or subtract with the fraction, it's the numerator that takes the negative sign. So you could rewrite it as -4/7 like this, okay? This is the same exact thing as, well, each other is, okay? And then, of course, you determine if it's necessary to add or subtract because it will show you. If it has subtraction with negatives, though, remember you're going to use keep, change just in the numerator part when you get to this point in order to change it into an addition problem. So here we go. This one's nice. This is a good way to start because this one is showing that the denominators are already the same. They are in fifths. Okay, so I'm gonna make a big old fraction right here in fifths. I see that the operation is addition, so I know I'm going to be adding. Well, what am I going to be adding? The 4 and 13 numerators. That's it. Okay, so when I do add those, I'm going to keep the denominator the same. 4 plus 13 would be 17. Okay. Now, usually at this point, some students will ask, why are the denominators, why isn't this 5 plus 5 is 10? It's because the denominator only tells you the sizes of the piece. The numerator tells you how many there are, which is why you'd have 4 of the fifths, you'd have 13 fifths of the fifths. That's why we're adding just the numerators here. The denominator is the size of the piece. It stays in fifths. Okay, so even when you add these two together, that tells you how many fifths overall you would get from just adding these two together. So we end up with 17 fifths on this one. Let's further emphasize this. This one we got a negative value. That's good. And again, this is a nice starter problem because the denominators are already matching as 9s. So even though the objective is that we can force those denominators to match right now, they're already matching, so we don't have to do any work in those terms, okay? Now, again, I would show this as -7 as the first numerator, and then the second numerator is 5. I can see the operation is addition, so let's go ahead and add those two together. Still in ninths though, that's -7 plus 5. I can see there's more negatives here than positives, which means my answer will be a negative. Then you just take the big number minus the small number. 7 minus 5 is 2. That's how negative my numerator is, -2/9. That will do. If I could simplify that, I would. And in the end, even on Canvas, you're always going to need to simplify those. If you do not, it will mark those incorrect. All right? So how do you type this into Canvas? Well, you type in -2, of course, you could say -2, and then the fraction line is the slash button and then 9, just like this. If you enter this fraction in this way into Canvas, you'll get it correct. But notice it's the 2 that's negative here, not the 9, because it's the numerator, all right? How about subtraction? Yeah, we can do some subtraction on this stuff. And I notice that the denominators are the same, so I can just start combining my numerators with subtraction. I have 7 first and then 5 second. So it is going to be 7 minus 5, which would be 7 minus 5 is 2. The denominator stays the same in eighths. Then we got to look here and see the 2/8. This one can be simplified. So we should always be checking in the end here to see if the value can be simplified. And it can. All right, so let's go ahead and simplify those. What are we going to simplify those by? Well, I know that 2 and 8 are both even at least. So I know they're at least divisible by 2. Let's start with that, see how far that takes us. So that's going to be a new fraction. It's not going to change the value of the fraction, just the way that it looks. 2 divided by 2 in the numerator is 1. 8 divided by 2 in the denominator is 4. 1/4. Yeah, once you get a 1 in either of the values, it's completely simplified, so that's it. Right there. 7/8 minus 5/8 ends up being, in the end, 1/4. Still subtraction. And so, and now remember, if these were negatives, we would look to change the operation into addition, but it's not. You just got a big number minus a small number. That's okay. So yeah, it's 18 minus 3 in the numerator. And again, we just change this into a big fraction like this because the sizes of the pieces are the same. We're just operating with just the numerators. So what do we get out of this? It's still going to be in fourths, but 18 minus 3, and if you need to stack and subtract that, that's fine. 8 minus 3 is 5. Drop the 1, 15. 15 fourths. And again, if this could be simplified, then I would, but it can't, so I won't. Now, you be careful because elementary teachers who have very good intentions most of the time, perhaps sometimes it's evil, I don't know. But in the past, they've probably told you it's not simplified until it's a mixed number. And that's probably because in real life, mixed numbers are more useful. But in a math class, we don't want those stinking mixed numbers, so don't put them. They always use an improper fraction like we have right here. So now we're going to see some problems that do not have common denominators from the beginning. We will force those to be the same ourselves, right? So, and that's the first thing we got to do when the denominators are not the same. You got to force them to be the same. That's pretty much what number 1 is telling us to do. Finding a common multiple. Now there's 2 formal methods for this. Make a list of the multiples of the 2 numbers, or you can use prime factorization, which we've done. I'm not going to use either one of these, all right, because we have kind of a shortcut method which gives us it guarantees common denominators every time, no matter what the denominators are, always. It will always give us common denominators. Okay, so that's the first step. Then you're going to scale the individual fractions accordingly, which is kind of part of what we're going to be doing. So I kind of combine these 2 steps. Then you perform your operation, and then in the end, once you're done with addition or subtraction, then you're going to be looking to simplify your fraction, okay? Now, right now, we're just focused on addition and subtraction. You'll keep in mind, because we're going to go over this in 3.2 today, when we start looking at multiplication and division of fractions, we do not need common denominators. You'll need to remember that because almost always, inevitably on a homework, on a quiz, on a test, someone will start to think that you have to have common denominators with multiplication and division. You do not. We only need common denominators with addition or subtraction. That's it. So on this one, yeah, we see that the denominators don't match. So here's what we're going to do. And we've seen this already. We saw this, I believe, in the last unit. So I see this denominator of 2 first, okay? I'm going to scale the second fraction by that denominator of 2 with multiplication, okay? So this is going to change the look of that second fraction. Still got addition here. And in the numerator, I got 3 times 2, which is 6. And then in the denominator, I got 5 times 2, which is 10. Now, if I do this correctly, I will get a 10 denominator in the first fraction as well, because I'm taking control of the fractions here by forcing this next denominator to be 10. If I haven't said this already, this is not a passive math skill. You're not waiting for the numbers to do something. You're forcing it to happen, okay? So the first 2, I'm going to take the second denominator 5 and multiply it by, or scale that first fraction, both the numerator and denominator, by that denominator 5. So in the numerator, 5 times 3, boom, 15. In the denominator, 5 times 2 is 10. See how we forced those 2 denominators to match? That's exactly what we wanted. So now that the denominators do match, then I can combine this into one big fraction like this, okay? So I'm going to take the 15 numerator and add the other 6 numerator. Still in tenths though. So 15 plus 6, you can stack and add those if you need to, but it's 21. So we scaled the fractions, forcing the denominators to be the same, and then we operated with the numerators, 15 plus 6. And the last thing we should do is to look to see if this can be simplified. Now 10 is divisible by 10, 5, and 2. 21 is not divisible by any of those, so that means this is fully simplified. All right, on this one, I'm going to do this twice because we got a couple different methods for this, okay? And some of you may see what I would do on the second method, which is I would consider it a shortcut, okay? But for now, let's just stick with the method that we have, okay? So I'm going to take this 4 denominator. I'll start with the 2, actually. 2 denominator, I'm going to scale the second fraction by 2. All right, so this is going to give me, you're still going to have 2 fractions being added together. But the second fraction, instead of 1/4, it now becomes, in the numerator, 1 times 2 is 2. In the denominator, 4 times 2 is 8. So 2/8, again, it maintains the same value. It's just showing a little different, that's all. And then for the first fraction, I'm going to scale that by the second denominator, which is 4. So I'd have 2 times 4, which is 8. So see how that forced those denominators to match? I just got to multiply the 13 by 4 as well. Now, some of you may know your 13 multiplication tables. Most students don't, so let's go ahead. 13 times 4. 3 times 4 is 12, carry the 1. 4 times 1 is 4, but adding the 1 is 5. So 52, that ends up being 52/8, which I will now add because the denominators match as 8ths. So we're going to add 52 and 2. Well, that's still an 8th, by the way, but 52 plus 2 is 54. So last thing we would want to do here is just to see if this can be simplified. Now, I know they're simplifiable by 2 because of the 4 in the 1's place value and the 8 in the 1's place value. They're both even, so I know these are both divisible by 2. I'll start with the denominator just because it's easier, but 8 divided by 2 is 4. But I'll have to do some long division with 54 divided by 2. So 54, I'll make that a little bigger. 54 divided by 2. 2 goes into 5 2 times. 2 times 2 is 4. When I subtract, I get 1 left over, drop the 4. 2 goes into 14, 7 times. So nothing remaining on that. But I get my quotient of 27, which is my numerator, okay? And last thing I want to do on this is just check. Can this be simplified? No, it cannot. Because 27 is only divisible by 27, 9, and 3. 4 is not divisible by any of those. So that is complete. Now, remember the objective here, if you can just kind of think for yourself here and not get so algorithmic that you just start doing things. Some of you would notice that the 4 is a multiple of 2. That's what I'm looking at in the second part, okay? Second method, you'll see that the answer is the same here in the end. What I would like here is for the denominators to match. But I know 4 is a multiple of 2, so if you wanted to, what you could do is just take that denominator of 2 and multiply it by 2. See that? But you'll have to scale the numerator the same way. So this will produce a new fraction. In the denominator, it's 4, right? So, and that's the whole objective here, is that we want the denominators to match. And right now, we're going to add this to 1/4. And they do match. But what is the numerator? Well, 13 times 2. I guess we can stack and multiply that. 13 times 2, 2 times 3 is 6. 2 times 1 is 2, 26. So 26 fourths plus 1/4. And now that the denominators do match in fourths, I can take my numerators, 26 and 1, and add them. And you see that we end up with fourths, but 26 plus 1, yeah, that's 27. And we end up, once again, with the same answer that we had before. Okay? Same answer, a slightly different method. Not method, but a slightly different procedure. Okay? So if you notice that one of the denominators is just a multiple of the other one, you can just multiply one of the denominators. You don't have to multiply both. Okay? Now, if you don't notice that trick, is it okay? Yeah, of course. You can see that we got the same answer. That's the crucial part. You can go through this whole process here and get the same answer, or you can take a little bit of a shortcut here, same answer. All right? All right, we got a subtraction problem now, and the denominators do not match. So I would just check, is 9 a multiple of 2? It is not. So we're going to have to use the same trick that we had from the beginning. I'm going to take my 2 denominator and scale the second fraction by 2, which will give me a new fraction. Now this is a subtraction of fractions. But the second fraction in the numerator, 2 times 2 is 4. In the denominator, 9 times 2 is 18. But then I take my 9 denominator and multiply or scale that first fraction there by 9. So in the numerator, 9 times 3 is 27. In the denominator, 9 times 2 is 18. So again, that forced the denominators to match right away. And I'm ready now to start combining the two numerators because the denominator stays the same. And this is 27 minus 4. Now do keep in mind, if this was minus negative, I'd use keep change on this, but it's not, it's just minus. And still an 18th, but 27 minus 4 is 23. Now always check to make sure that the fractions, if they can be simplified, then do it. If not, then just leave it. And I know 23 is prime. 18 is divisible by 2, 6, 9, and 3, but 23 is not divisible by any of those. So this one's done. There we go, another subtraction problem. And the denominators don't match, and they're also not multiples of each other, so this is the old-fashioned way. A little bit more space there. Okay, so the 7, we're going to scale the second fraction by 7. And if you wanted to, some of you just kind of look at this right now to scale the first fraction by 5. Either way. The idea here, though, is that your denominators will need to match. So I'll start with the second fraction, just like we usually do. In the numerator, 3 times 7 is 21. In the denominator, 5 times 7 is 35. The first fraction has in the numerator 5 times 12, which is 60. And in the denominator, 5 times 7, see, there's the 35. So we forced those to match, and now we are ready to subtract adjust with the numerators, which is 60 minus 21. So let's go and stack and subtract those. 60 minus 21, we'll make that 10 and borrow from the 6. 10 minus 1 is 9. 5 minus 2 is 3, 39. Okay, so let's a little bit more space here. Still in 35ths, by the way, but in the numerator I get 39 from the subtraction. So 39 35ths. I know 35 is divisible by 35, 7, and 5. 39 is divisible by none of those. It's divisible by 3, but not 7, 5, or 35, so that's it. That one's considered fully simplified. Now, if you end up with a regular value being operated with fractions, then what we want to do is change it into a fraction, because you can. Okay, if you take a number like, let's say 12, you can make it 12 over 1 if you want. In fact, that divided by 1 was always there. That's what this is. That's kind of this identity property for division. You can divide anything by 1 and get itself. Okay, so 12 divided by 1 is still 12. but we're going to need to see these fractions because we're going to be operating with fractions, okay? But keep in mind that, again, that divide by 1, you can make it go away. You can make it a phantom 1 like this. It's still there. It's like the stuff that we had is still there. It's just lurking in the shadows, watching always. And again, that's what makes these phantom values so creepy. So, you know, right here we're saying we do want to see that value. We don't want it to lurk in the shadows anymore. That's the whole point. So when we see a problem like this one, even though it's subtraction, it's not the subtraction that matters. It's that we want to make the 6 a fraction over 1. Now, the nice thing about 1 denominators like this is that every other number is a multiple of 1. So that means that I don't need to scale the second fraction. I can keep it the same, all right? I just need to scale the 6 over 1. So we're going to subtract this by 15/8. So the 1 denominator, I can make it an 8 by just multiplying by 8. Boom. Common denominators, right? But I got to do the 6 times 8 as well. 6 times 8, 48. All right, now that I got that, I'm now ready to combine my two numerators there in eighths. With subtraction, it's 48 minus 15. And this will give me a new fraction in eighths, but 48 minus 15. 8 minus 5 is 3, 4 minus 1 is 3. All right, 33 eighths. That looks good. And last thing I do is check to see if this can be simplified. 8 is divisible by 8, 4, and 2. 33 is divisible by none of those, which means that this is complete right here. Billy bought 2 pizzas. He ate 3/4 of one because he couldn't finish one. Wuss bag. How much pizza does he have left? Okay, well, here's the thing is a pizza, he's got 2 pizzas to start out with. So there's my 2 pizzas, okay? Now it says he's gonna eat, that's subtraction, is 3/4 of one of them. So we're gonna subtract 3/4, okay? Then how much pizzas does he have left? That's what this will equal in the end. So I'm gonna make this 2 over 1 and scale that fraction. The second part of this is gonna stay the same, right? So I just gotta scale the 2 over 1. That will give me a new fraction because I know that everything is a multiple of 1. So 1 times 4 there in the denominator will be a matching denominator 4. But I gotta do the same thing to the numerator. 2 times 4 is 8. 8/4 is 2. Yes, it is. And now I'm ready to combine my 2 numerators because the denominator stays the same as 4. So that's 8 minus 3. Try to match these colors. So in fourths, what is this? In fourths, well, 8 minus 3 is 5. Now the answer is not 5/4, by the way, although you may have thought it was. This is a word problem, so make sure you label this one. I'm going to say it's in pizzas. And that's good enough. All right, there's our objective for 3.1. I can force denominators to match so that I can add and subtract fractions. Hopefully we're feeling pretty good about that.